Hey guys, welcome to 6.4, Quantifying Heat and Work. This is actually going to be split up into two sections. We're going to talk about specific heat in this section, mainly this formula, Q equals mc delta T. And in the next section, we're going to put it together and we're going to talk about thermal energy transfer, and we'll get to that when we get to that. So working on 6.4, Quantifying Heat and Work, first off, we need some basics, and we need to remember that heat is the exchange of thermal energy between a system and surroundings, and we're trying to reach a thermal equilibrium. We'll define that in just a second, and I want you to always remember that we're going to be going from a high temperature to a low temperature. So that brings us to thermal equilibrium. What is thermal equilibrium? Take a couple of seconds and try to figure out a definition. Thermal equilibrium is just as it sounds. We're trying to get the same temperature for both substances. So basically, we're looking for a happy medium. So somewhere they're going to meet in the middle. So same temperature for both substances. And this is just talking about our flow of heat or our flow of thermal energy. Experiments show that heat absorbed by a system and its temperature change are directly proportional. So that means they're related to each other. And this constant of proportionality is called heat capacity. And we're actually going to be doing calculations with heat capacity. And in this book, heat capacity is abbreviated capital C. You may have seen it abbreviated different in different books, but for our book it's capital C, and on the AP test it's also capital C. So that brings us to heat capacity, and heat capacity is a very simple definition. It's the amount of energy required to raise the temperature. And usually we're talking about 1 degree Celsius. So we're talking about how much energy it takes to raise the temperature of a substance by 1 degree Celsius. So let's think about that in common terms. Let's say we're going to make our mac and cheese. We put our pan or our pan on the stove and we heat it up. All right, and this is before we put any water in it, and so immediately we're heating it up. The pan gets really hot. And then you start to add the water, and what happens? The pan's still really hot, but the water takes forever to boil, especially if you're really excited about your mac and cheese. So what happens is we have our pan sitting on the stove. And yes, I'm going to be an amazing artiste here. We've got our flame underneath it, heating it up. And the pan, since it's made out of metal, it has what we would call a low heat capacity. It doesn't take very much energy at all for it to heat up. But then, once we add the water to it, alright, it starts taking forever to heat up, and that's because water has a very high heat capacity. And so there's our example. So let's move on and talk about specific heat capacity. And specific heat capacity is just, again, really specific. It's the amount of energy required to raise the temperature 1 degree C. But in this case, we're talking about for 1 gram of substance. So now we've got like a quantity of it, and that makes sense to us. And a lot of times we actually use specific heat capacity. It's abbreviated C sub S, and we use specific heat capacity so much more than heat capacity and molar heat capacity. But we should go ahead and define molar heat capacity. What do you suppose molar heat capacity is? Molar heat capacity is the amount of energy to raise the temperature of 1 mole. Of a substance. So it's talking about how much energy it takes to raise the temperature of 1 mole of a substance. Now, that brings us to a very interesting conceptual question. Why does California have such a mild climate? We know that some specific heats, there's a table of specific heats listed, but up here we talked about, in this example up here, we talked about metal having a very low heat capacity, aka a specific heat, but water having a very high specific heat. So California has a really mild climate because it's surrounded by water, and that water keeps the climate pretty mild. It keeps it from going too high or too low. Now on to this very important formula. This formula is something that you will use on the AP exam. It shows up just like this. You don't have to memorize it because it is on your formula sheet, but let's talk about what each of these means. So we've got Q, which hopefully we remember is heat, all right? It is measured in joules. M we haven't seen yet in this chapter, but it is mass, and it is measured in grams. C is our specific heat. And if we want to be really specific, it's actually specific heat capacity. And remember, it's a constant, so it's constant for whatever substance we have. And its measure is joules per gram degrees C, or K, depending on what we've got. And our delta T, remember I told you to remember delta always means change. So we're talking about our change in temperature. And so we're going to take T final minus T initial. And that's how we find delta T. So let's see if we can't do an example real quickly here using that formula. So we've got, suppose you have a penny minted before 1982 when pennies were mainly copper. Right now they're quite a bit zinc and a little bit of copper. So we're now going to talk about mainly copper. How much heat is absorbed? We found a penny in the snow. How much heat is absorbed as the temperature, as it warms up from negative 8 degrees Celsius to the temperature of your body, 37 degrees Celsius. And we're assuming the penny is pure copper and has a mass of 3.10. So take a couple of seconds, write down the important facts, and I'll be back with you in just a second. All right. Hopefully you've had a chance to write some things down. So what I like to do when I work a problem like this is I just like to write what I know. Q is what we're looking for. How much heat is absorbed? So that's going to be my question mark. So I just continue on my little formula right here. Next up is M. Do I have a mass? Yes, my mass is right here, 3.10 grams. Moving on to C. C is our specific heat. This is something we had to look up, and it is 0.385 joules per gram degrees C. And now our temperature change, delta T, is we're going to take T final minus T initial. So we've got 37, which is our final temp, and we're subtracting a negative 8. So that's going to give us 45 degrees C. So now we're ready to just plug this in and solve. And we can write it all out here. Q equals 3.10 times 0.385 times 45, and our answer will be in joules. And with sig figs, we've got 3, 2, so we're going to say Q equals 54 joules. Should be our answer there. And last but not least, conceptual connection. Suppose you are cold weather camping and decide to heat some objects to bring into your sleeping bag for added warmth. You place a large water jug and a rock of equal mass near the fire. Over time, both the rock and the water jug warm up to about 38 degrees C, which is about 100 degrees Fahrenheit. If you can only bring one into your sleeping bag, which one do you choose to keep you warmer and why? Take 30 seconds to think about that, and I'll be back with the answer and finish this section. Well, what did you think? Hopefully you chose the water jug. The water jug, water, we said earlier, has a very high specific heat, so it's going to take more energy to get warm, but if it's the same temperature, then it's also going to take longer to cool down. And that makes sense if you think about your hot pan after heating it up. It cools down much faster than the water on the inside. All right, thanks for listening.